An induction generator or asynchronous generator is a type of alternating current (AC) electrical generator that uses the principles of induction motors to produce power. Induction generators operate by mechanically turning their rotors faster than synchronous speed. A regular AC asynchronous motor usually can be used as a generator, without any internal modifications. Induction generators are useful in applications such as mini hydropower plants, wind turbines, or in reducing high-pressure gas streams to lower pressure, because they can recover energy with relatively simple controls. An induction generator usually draws its excitation power from an electrical grid. Sometimes, however, they are self-excited by using phase-correcting capacitors. Because of this, induction generators cannot usually black-start a de-energized distribution system. An induction generator produces electrical power when its rotor is turned faster than the synchronous speed. For a typical 4-pole motor, 2 pairs of poles on stator operating on a 60 Hz electrical grid, the synchronous speed is 1800 rotations per minute (RPM). The same 4-pole motor operating on a 50 Hz grid will have a synchronous speed of 1500 RPM. The motor normally turns slightly slower than the synchronous speed. The difference between synchronous and operating speed is called slip and is usually expressed as % of the synchronous speed. For example, a motor operating at 1450 RPM that has a synchronous speed of 1500 RPM is running at a slip of plus 3.3%. In normal motor operation, the stator flux rotation is faster than the rotor rotation. This causes the stator flux to induce rotor currents, which create a rotor flux with magnetic polarity opposite to stator. In this way, the rotor is dragged along behind stator flux, with the currents in the rotor induced at the slip frequency. In generator operation, a prime mover, turbine or engine drives the rotor above the synchronous speed, negative slip. The stator flux still induces currents in the rotor, but since the opposing rotor flux is now cutting the stator coils, an active current is produced in stator coils and the motor now operates as a generator, sending power back to the electrical grid. An induction machine requires externally supplied armature current. It cannot start on its own as a generator. Because the rotor field always lags behind the stator field, the induction machine always consumes reactive power, regardless of whether it is operating as a generator or a motor. A source of excitation current for magnetizing flux, reactive power, for the stator is still required to induce rotor current. This can be supplied from the electrical grid or, once it starts producing power, from the generator itself. Active power delivered to the line is proportional to slip above the synchronous speed. Full rated power of the generator is reached at very small slip values, motor dependent, typically 3%. At synchronous speed of 1800 RPM, generator will produce no power. When the driving speed is increased to 1860 RPM, typical example, full output power is produced. If the prime mover is unable to produce enough power to fully drive the generator, speed will remain somewhere between 1800 and 1860 RPM range. A capacitor bank must supply reactive power to the motor when used in standalone mode. The reactive power supplied should be equal or greater than the reactive power that the machine normally draws when operating as a motor.